Swayam Prabha. Digital India. Educated India.
So, we are going to be talking about the last slides for last lectures, lecture 6. I think it says lecture 5 on the manual, on your thing, but it's lecture 6. We're going to do the advanced methods. So, I'm going to start with just one today, and then we're going to do few tomorrow. So, I'm going to start with the many objective one, which is NSGA 3. All the other thing that you see, some of them I put in black, we're not going to do, we'll probably not have time. I will already talk about distributed computing, right, with different cones. Then there is dynamic EMO where the Pareto front is changing. The problem is changing with time. We also have ways to solve them. You find some objectives are correlated to each other, so you can reduce the objectives. So that's something also can be done. Can we say how far we are from the theoretical Pareto set without optimizing and knowing where the theoretical Pareto front is? So looks like if you have the gradients available for your objective function and constants, you can do that. You can have an estimate of not the actual distance, but relatively speaking, like if I give you two solutions, and you can then say this solution is closer to the Pareto set than the other. At least that much you can say with the existence of gradients. Again, because of time, we're not going to go into all that. You have a Pareto set, but each point in the Pareto set can come from multiple designs. So if you take different, like multimodal problems, right? You have the same objective function. Now in this case, you have same two objective function values. F1, F2 is identical for both of them. So you are not interested in finding just one, you are interested in finding both. That's called multimodal EMO, and there are some research that goes on. This happens in design many times, and we are interested in that. So all the things are in red, we'll try to cover, and we'll talk about them more tomorrow. But let's start with this many objective. First of all, why do we call it a different name? Not multi, but many. That's because we've seen NSGA2, SPA2, these kind of methods, they work for 2 and 3 objectives very nicely because it's fast and because the way we have got the diversity preservation mechanism working, that's specific to these methods. If you take NSGA2, try for 4 or more objectives, that crowding distance idea of fitting a box in the neighborhood doesn't work so well because it's higher dimensions. Sorting along each objective axis doesn't make them neighbors. Okay, so it kind of loses the meaning of that, and we start to see the performances are not so good. So we've been thinking, because NSGA2 was developed in 2002, and we've been since then doing lots of things. Not until almost 2010 when we had the idea of NSGA3, and then it took us some time to work on it. The paper got finally accepted at 2014 called NSGA3. Because the algorithm wise they are very different methods. You have to consider higher dimensions, so very different methods. We wanted to differentiate these two optimizations. So 2 and 3 we call multi-objective optimization, more than 3 we call many objectives. So you might see some papers with title that says something about many objective optimization. That means they are talking about more than 3. Okay? Yeah. So what are the difficulties? One I already mentioned, but there is another reason of why multi-objective do not work for many objective algorithms, is that a large fraction of population gets dominated. Let me explain with a figure here. So this figure is generated based on random initial population. So let's say I've randomly created 100. So when I do n equal to 100, let's say 100 members with 2 objectives. So basically 2 columns of 100 rows each, randomly created between 0 and 1. And let's say first one is my first objective, second one is my second objective, and I want to find the non-dominated set, the set that do not get dominated by anybody. And I notice that when I calculate that on the random population for 2 objectives for 100, about 5%, that means 5 out of 100 belong to the non-dominated set. Another 95 are dominated by them. When I go to 4, now I have 4 columns randomly created again, and I count how many of them are non-dominated. It turns out about 40% of them are now non-dominated. When I go to 10, about 95% of them or more are non-dominated. So you see the effect that number of objective does to the set of the non-domination. So when you have more and more objectives, there are more ways you can become non-dominated, and then more and more proportion of your population is already non-dominated. So now if you say that I am going to move my good solutions, which are non-dominated solutions, to the next generation, in case of 10 objective, 95% of your population you are supposed to move. That's a lot. Okay, then only 5% slot is there for new solutions. So your search slows down like anything. Okay, so if you look at the NSGA 2, if you apply your PT and you create your QT and you combine them into one, 95% of them are in F1. So you barely go to F2 and have to pick just 5%. So very few new solutions you can put in, and that's a problem. So that's the first thing we are talking about here. And then of course when you have higher number of objectives, maintaining diversity means crowding distance do not work. So you need to now think of clustering or a diversity distance metric in higher dimensions, and we already know from the data analytics literature that that's a difficult thing to do. So that's a problem. Moreover, when you have higher number of objectives, if you take 2 points at random for crossover, chances are that they are picked from different parts of the objectives, the objective space, rather also from the Pareto set or rather non-dominated set. And then when you do a crossover between 2 very disparate solutions, you are not going to create something very useful, right? So your recombination operators are not that efficient. You got to do some kind of mating restriction, like if you pick one, another one, you cannot go far away from it in order to have a crossover. So all these complications come in. And then of course the other issues like representing, visualizing higher dimension is always difficult, but that has nothing to do with the algorithm. But you also need more and more points to represent a higher dimensional surface. Actually you need exponentially more points. If you increase by 1 dimension, 2 dimensions, maybe 20 points, you could do a nice distribution. If you go to 3 dimensions, even 30, 40 points is not enough, because it's a surface now, you need to go to the tune of 100. If you go to 3, maybe to the tune of 500 to 1000. So by the time you are 10 objectives, you probably need hundreds of thousands of solutions to really represent well a 10 objective problem. So that means your population size have to be hundreds of thousands, right? Then only you get that many points. So your algorithm will slow down a lot. Plus, okay, you get these 100,000 points, you cannot send all of them to decision maker and say, look at it, do pairwise, 100,000 choose 2 is a large number, so they don't have time for that many. In fact, there is a paper that's wrote by some MCDM people. They say 5 plus minus 2 is the number of points that the decision maker are comfortable looking at. So which means 3 to 7. So we cannot do 100,000. We cannot even do 10 or 20, right? So you can find 100,000, but then you have to cluster them down to maybe maximum 7. So all these difficulties are there. And then if you are comparing this set with another set having 100,000 solutions, it's always difficult to compute these performance metric and the visualization I talked about. So all these associated problems are there when you go to more than 3, but we need to handle. If there are 5 objectives the problem comes with, you have to handle, right? So we need methods, and these earlier methods don't work so well. So back in 2008, there are 2 gentlemen from Hong Kong, Ching Fu and his student, what's his name? Lu, I think. Anyway, I'm mentioning Ching Fu's name. He came up with a method called MOEA-D. MOEA/D. It's called multi-objective evolutionary algorithms with decomposition. Okay. So his idea was that we are going to decompose the entire Pareto set into like maybe 10, 20, 50, depends on your population size. That many partitions. Okay, how? He said we're going to have some lines, okay, that are going from ideal point towards the objective space, okay? And then our goal would be that every population member should cling to one of the lines and move down to the Pareto set. So if I make the lines uniformly distributed and I expect every member, one population member, to go through these lines to the Pareto set, I will have a nice distribution. So we've done a lot of stuff until that point, and none of them was working so well. As you increase the number of objectives, we have few papers actually that says it's not working. We did some fix up. It goes up to 5 objectives, but beyond that it's not. So he and our lab independently figured this out, that we need to have some kind of guidance. So we started the work around that time, and around 9 or so, my student, we did that and we said, let's see if there's anything out there to compare our method with, our NSGA3. We didn't call NSGA3 at that point. And he saw Ching Fu's paper. And he said, sir, maybe this algorithm may work, and it has this line concept which you also have. Then I know this guy, so I wrote to him. Oh, before that, I asked my students to code his algorithm and run on our problem, compare with ours, it works. Okay, so I wrote to him that, hey, did you know that your method can go more than 3 objectives? Because his paper was published by then and it was only 2 and 3 objectives. So I thought he may not have realized it. Then he wrote me saying, yeah, we just realized that it works. So his goal was not to find more than 4, but to just have another alternative to NSGA2. But unknowingly, his method could scale up because of this line thing. But there are some parameters and all that you have to say. In his case, you have to set 3 parameters. And we wanted to have no parameters. So almost independently, we found the idea, but the algorithms are completely different. It's good that sometimes you don't look into the literature. You just do it your own way, because you can get biased otherwise. But so let me explain NSGA3, and then tomorrow we'll talk a little bit about MOAD. Okay. So what is it? Let me take an example of this room. So let's say that corner is my ideal point. We have F1 increasing this way, F2 increasing that way, F3 increasing up. So you can physically visualize what's happening. So these are my objective functions. Objective functions can be negative. But if we put that as an origin, then you're talking about only positive octant, the first orthant or octant we are talking about. But if you have negative values, then your points will go to the other places, but we can always normalize, right? So that our best is at 0, worst is at 1. So we are always in the first octant. So that's a simple thing we could do. So now we can focus on this octant where we are all sitting. So your points, your objective values, when you compute from X, they are all over this space over here, right? First octant. Now the idea here is, think of a plane that is making equal angle to each of the axes. Okay, there is a plane, hyperplane, or in this case consider a plane, which is making equal angle to all. That means that plane is cutting the F3 axis at 1, F1 axis at 1, F2 axis at 1. This is this plane that I am showing. So it will be an inclined plane, equiangle to all the axes. It's a triangle, right? You see that? Okay. Now I'm going to put uniformly distributed set of points on this plane. We are looking, finally we found there is an approach called Das and Denis approach, where if you are not fussy about any arbitrary number of points, you say with certain structured number of points, you can do such a distribution. You see, between any 2 neighboring points, they have exactly the same distance. This distance is same as this distance is same as this, you can do that. Unfortunately, the total number of points has to satisfy this. What is that? M is the number of objectives. So in this case, let's say 3 objective, plus P is how many gaps do you want. So here I have 4, right? So P is 4 minus 1. So this is equal to 6. Choose P. P is again 4. So what is 6 choose 4? 6 times 5 by 2, 3, 15 points. So if you want 15 points uniformly distributed in this hyperplane, I can do it by Das and Denis method. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Exactly 15 points. If you tell me no, I need an even number, I need 16. This method cannot handle. It's structured. What's the next one? Next higher? I have to increase P by 1. So now instead of 4, I need 5. So let's do that math. 3 plus 5 minus 1, choose 5. And that's 8 minus 1, 7, choose 5. What is that? 7 times 6 by 2, 3, 21. So there is nothing in between 15 and 21 you can create. Next one in higher is going to be 21. So then there will be 21 points here. If you are not so fussy about these numbers, you can use das and Dennis. And for a long time we had to just follow these and uniformly create a set of points. Yeah. What is? P is the number of gaps between 2 points in every axis. So you see here how many gaps? 1, 2, 3, 4. Or how many points you want here? Minus 1. That's P. So if you have more gaps, you'll have more points. That's the thing. Okay? And M is the number of objectives. So that's a structured way we can actually create uniformly distributed set of points. So I can create that. Later on, I think in 2020 or so, we came up with a method where you can give me any number. I can give you almost uniform set, because there is no optimal, I mean, if you give me any arbitrary number like 16, there is no way I can have exactly the same distance from each other in the neighborhood. So there will be almost the same, but not. So we use the energy minimization concept to locate these points, but I could do 16, 17, any number you give me, we could do. So we have this now with coded in PyMu. It's in PyMu, you could do that. So you can choose any population size. Okay, so let's keep with this 15 or 21. So once you have these 15 points identified on this plane, this is a unit simplex because it kind of cuts them into 1, 1, 1. It's called unit simplex. Now that I've got these 15 points on this plane, what I could do, I can join from the origin to each of these points and have a vector. So now suddenly you see there are 15 vectors that are coming out, okay? And because it's covering the entire first octant, any point, normalized points can be in this space, and I can project it onto the plane. So I can happily work with this kind of space. Now 15 means at the end, my Pareto set may be somewhere here. It may not match with the plane, because if you have a linear hyperplane and the entire surface is available, then it will fall on that unit simplex after normalization. But any other Pareto front will not. But then each of these arrow, if I continue, it's going to hit my Pareto set. And my goal is to get wherever it's hitting that Pareto set, my goal is to find each of them. Because these points are uniformly distributed, the arrows are uniformly distributed, where they're going to hit the Pareto front is not going to be uniformly distributed, but it'll have a very good distribution. So that's the idea. So our goal is to now decompose the whole algorithm so that parallelly we go along these lines and go all the way to where the Pareto set is, because below that there is no solution, right? So that's a totally different philosophy because you are dealing with higher number of objectives. It's like NSGA 2. If you have multiple, if you have lots of points, you divide them into different fronts. First front is accepted. If there is room, second front is accepted. If there is room, third front. A point will come when you cannot take everything, then you have to do some kind of choice of which one I have to keep, right? So until that point is fine. We don't have crowding distance. Now the last front that we are stuck, we cannot take everything. So let's say we've got 10 points in the last front, we can only take 6. Which 6? We used to do crowding distance for that. Here what we do is we first, so let's say there are these 3 points and there are more points over here, 10 points there, and I have to choose 6 out of it. First thing we do is identify the extreme points of this set. They're all normalized first. So you see this can be somewhere, my plane can be somewhere 1, but this one, even after normalization, I think this may hit at 1 or something, but let's say that this is any other number. Let's say I haven't done the normalization. Then I find the extreme points of this set, and then make a hyperplane. So if there are 3 objectives, I need to find 3 extreme points to pass a plane through them. Other points may not be falling on the plane, but I just continue that plane, extend it till it hits the axis. Okay? And they're going to hit into these A1, A2, A3, and now we normalize all the points based on 0 to A1. So A1 will become 1, and A2 will become 1 on F2 axis, A3 will become 1, at this point will become 1 on the F3. This is how we normalize. We don't look at mean, max, mean, max, mean, max. Mean is of course there, but the max is not the max of these values, but rather we fit a curve, we put a plane through them and then see where this plane is hitting the axis. Because I may not have a point on the axis, right? So extend it, and then I get the intercept, and with that I say this is my upper bound. Now we can normalize based on that. Okay? After I've normalized, so these are all 1, 1, 1. This is my hyperplane and these are my points, you see. Their upper bound is never going to go beyond 1 now. So these are my population, these circles. Now what I do is I go line by line. I consider one line at a time and then next line, and identify which of the population member is close to each line. So for example, this point I compute the orthogonal distance to the line. Now they are all normalized, so I can compute all the distances. This point distance is computed from first line, this point distance is computed from second line, third line, fourth line, and I figure out which line has the shortest distance, which means this point is associated with that line. This point is associated with this line. This point is associated, which one? This point is associated with that line. So we always find the shortest one for the association. Once the association is done like that for every point, population member of that last thing that I could not take in, then what I do is I start from the first one and I pick the associated member. It could be that some lines I've got more than one associated member. Okay? Then I pick the one with the smallest distance out of the two. So the idea is we go line by line, we pick the one that is closest to each line. Once I'm done with that, if I have still more room in my population to be taken, then I do a second round. I take the second closest and continue till I can. That's it. So instead of crowding distance, we actually go by the line, and then we are picking up the closest point for every line. Because we are giving equal importance to each line, one point, then next line, we are maintaining diversity. And the lines are well diversified beforehand, so we are maintaining diversity. So we avoid calculating crowding distance and everything, but it's just association, normalization of the points, population members to this unit simplex level. So I can compare every population member with these arrows and figure out which one is close to each of the arrows. Does that make sense? Okay. Another thing in NSGA3 is, if I need 50 points, I will use 50 lines. Okay? Because I am using 50 lines and every line I am expecting 1 point, we don't need to have any selection. Because if you do selection between 2 points, we are saying, is this line more important than that line? We don't want to go into that. We want to find 50 points, so there is no tournament selection. Okay? We only do recombination and mutation after that and create a new population, combine with the old population, again do non-domination ranking, first one, second one, like that we do. Pretty soon what happens, as I showed you, when you go to 5 objectives or so, already 40-50% of the population are in the first front. So very quickly, like after 3-4 generations, all your 2N population or maximum of 2N population members, most of it are in the first front. So we are doing this kind of association business only with the first front, and you are not able to pick anything from the second, third front because there are not many points there. So that's why this is so important, that what you do with this last front becomes your default very soon, and that's why you got to spend all your ideas for that. How do you handle this very last front? Okay, again, there is no parameter that I talked about, no parameter anywhere, right? So it's like an SGA2, but then with decomposition concept. So no selection operator, recombination mutation as usual. Sometimes we could do a mating restriction for very large number of objectives, but our NSGA3 code, we don't have that explicit. But in some problems we work with industry, we do that. Yeah, so this to have meaningful offspring. And population size is no more a parameter that you have to set. It depends on how many points you want to find. And that's usually dictated by the user or the problem description, how many points you want to find. No additional parameter needed. Okay, so that's it. And you can see some results. This is on 3 objective. See how nice a distribution. Here I have 91 lines. 91 falls into the Das and Dennis number. And you can see how nice a distribution you can get. Okay. You could also do very few. Like here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points in the entire surface. So all you have to do is supply these 10 Das and Dennis points, arrows, and it will find them for you. You need not find the whole thing. You say, I'm only interested in finding the middle part, because that's where all the trade-offs are. So yeah, you specify your reference points there to have those lines, arrows, and you will find it there. You can have constraint problems, like this constraint problem make this part infeasible, as you see, and we didn't find. This is the feasible part, another feasible, feasible, feasible. You are giving points all over because you don't know where the feasible region is. So many of those arrows will not have an associated member. So at the end you will not have any member for those, but you will have multiple members for them, but at the end you just present the ones that's closest to them. Okay. You have a problem where your Pareto set comes from one surface, constraint surface, another patch comes from another constraint surface. It's all great. You see how nice a result. 10 objective, you can see how good a distribution with the parallel coordinate plot you can see. There's crisscrosses, there are 0 to 1, all of them going. MOEAD results are not as good. I'll probably show you tomorrow. This is a water problem, a water distribution problem with 5 objectives, and we have lots of these. Again, you don't see this well, but then, yeah, this is a simulation of how the NSGA 3 points go to the Pareto set and shows you that nice distribution.